So finally, let's look at some examples of using residue theory to evaluate real integrals, like the ones that are on your honors worksheet. This type, which are going to be rational functions of sine and cosine, correspond to problems similar to numbers 6 to 10 on your list. So, for example, let's see if we can find the integral from 0 to 2 pi of 1 over 13 plus 12 cosine theta d theta. So when I say a rational function of sine and cosine, I mean a fraction where the top and bottom are polynomials in sine theta and cosine theta. Now, before we dive into this, we need to do a little bit of warm-up theory for all of the problems of this type. First of all, this is an integral along a piece of the real line. We want to change this into an integral over a certain curve in the plane, in the complex plane. And what we're going to do is integrate around the unit circle in the complex plane. So I can parameterize a unit circle using x equals cosine theta and y equals sine theta. So z, which is x plus I times y, will be cosine theta plus I times sine of theta. And you might recognize that as being Euler's formula. This is the same thing as e to the I times theta. So z equals e to the I theta, with theta going from 0 to 2 pi, is a parameterization of this circle. One lap going counterclockwise. Now, in problems like the one we have over here on the left, we need to be able to isolate the sine theta and cosine theta. So let me show you some tricks for that. Notice that 1 over z, I'm going to move over the left a little bit. Notice that if z is equal to e to the I theta, then 1 over z is the same as 1 over e to the I theta, which is e to the negative I theta. So if e to the I theta is cosine theta plus I times sine of theta, then e to the negative I theta is cosine of negative theta plus I times sine of negative theta. Cosine is even, so cosine of negative theta is the same as cosine of theta. But sine is odd, and sine of negative theta is the same as negative sine of theta. So let's capture what we've got. We have that z is cosine theta plus I times sine of theta, and 1 over z is cosine theta minus I sine theta. Look what happens when we add those together. Z plus 1 over z is equal to 2 cosine theta, and the signs cancel out. So cosine of theta is the same as half of z plus 1 over z. So in an integral like we have over on the left, I'm going to be able to replace the cosine theta with 1/2 of z plus 1 over z. Now let's see if we can isolate the sine. I'm going to do something similar, only instead of adding z to 1 over z, I'll take z minus 1 over z. Look what happens there. If z is cosine theta plus I times sine of theta, then negative 1 over z, I'll change the signs here, will be negative cosine theta minus I sine theta, plus I sine theta. So z minus 1 over z, the cosines cancel this time, and I get 2I sine theta. So that means that sine theta will be 1 over 2I times this difference. And we almost have our dictionary. The last thing we need is we need to know what we can substitute in for the d theta. So let's work a little bit to the left, and then I'll collect this into a dictionary. If z is e to the I theta, then the differential dz is going to be e to the I theta times the derivative of the inside, which is I d theta. But remember, e to the I theta is the same as z, so this is I times z d theta. So d theta is the same as dz over iz. So the four boxed equations I've got, together with this, are going to be the dictionary, which allows us to change integrals like this into integrals around the unit circle. Let me erase a bit, capture this information, and then we'll actually attack this problem. There. So that's the dictionary. On the unit circle, z is equal to e to the I theta. Cosine theta is half of z plus 1 over z. Sine of theta is 1 over 2i times z minus 1 over z. And d theta is equal to dz over iz. And if I want to go around the circle exactly once, counterclockwise, I'll let theta go from 0 to 2 pi. So let's see what happens when I make those substitutions in here. Instead of integrating from 0 to 2 pi now, I'm integrating around the circle C. I have 1 over 13 plus 12 times cosine theta gets replaced by half of z plus 1 over z, and d theta gets replaced with dz over iz. Now this is an integral in the complex plane. The 1 over I can factor to the front. Notice that the 12 times the 1/2 I can simplify to make 6. Let's do that right here. So that my denominator is 13 plus 6z plus 6 over z multiplied by dz over z. And then if I want, I can distribute this z in so that I have 1 over I integral around c of 1 over 13z plus 6z squared plus 6 dz. I'd like to rewrite this in descending order. That'll give me 6z squared plus 13z plus 6. I'm going to rewrite that a little bit bigger. Cool. Now to apply the residue theorem, I need to know where the poles are for 6z squared plus 13z plus 6. And fortunately, this polynomial factors. it factors as 3z plus 2 times 2z plus 3. Now let's see where the poles are going to be. If 3z plus 2 is equal to 0, then that means that z is equal to negative 2 over 3. If 2z plus 3 is 0, that means that z is equal to negative 3 over 2. So I have two poles, one at negative 2/3 and one at negative 3/2. Now as far as the unit circle is concerned, here's negative 1. So negative 2/3 lies somewhere around there. Negative 3/2, though, lies outside the unit circle. So when I apply the residue theorem, I'll get 1 over I times 2 pi I times the residue of the function just at the pole which is inside the circle. So this is going to equal 2 pi times the residue of f at the pole negative 2/3, where this is my function f. So let's do some scratch work and find out what that residue is. The residue of f at negative 2/3 is going to be the limit as z goes to negative 2/3 of z minus negative 2/3, so z plus 2/3, over 3z plus 2 times 2z plus 3. Remember the formula I'm using is the limit as z goes to z naught of z minus z naught times f of z. Now this is actually an indeterminate form. If I plug in negative 2/3, I get 0 on top, and I also get a 0 on the bottom. So that I can cancel, let me maybe factor a 3 out of this 3z plus 2. That'll give me 3 times z plus 2/3 and now you can see that that z plus 2/3 cancels from top and bottom. So I have the limit as z goes to negative 2/3 of 1 over 3 times 2z plus 3. Using direct substitution, that's 1 over 3 times, plugging in negative 2/3, negative 4/3 plus 3. Distributing the 3, I have negative 4 plus 9, which is 1/5. So, substituting that answer back in over here, my integral is going to equal 2 pi times 1/5. And that's my answer.